importance in field of security. That's why we have included health and stealth and energy sectors in our chapter. This stealth is nothing but low observability. Stealth technology means that is like invisibility. There is a lot of difference between the detection and invisibility. People will try to detect, but people will try to become invisible. This invisibility is nothing but low observability or stealth. This after Second World War, the stealth word has become a famous, and now each country is spending money for stealth technology. Stealth technology is invisibly attacking on enemy. This is one of the important terms. Even we see the recent trend. It is we might be knowing the value of invisibility. Low observability can be done by these parameters. One is vehicle shape, avoiding right angles to the metal plates, and chemical composition of material, and radar absorbing materials, and plasma stealth technology. Within these technologies, we are using our carbon materials. This is about stealth technology. Now, if you come to our chapter, that is Unit 4, this we are going to discuss about introduction to the carbon materials, fullerenes and synthesis, production properties and applications of fullerene. If you come to the periodic table will tell us the physico-chemical properties of any element will be depending on electronic configuration. That means electron will decide the physical and chemical properties of material. That means electron play a major role, electron movement will play a major role. By reducing the size of a particle to the nano level, we can control the movement of electron. That's what nanoscience and nanotechnology has become one of the important field in nowadays, particularly in the carbon materials. That is, the 20th century is a silicon century. That means we are depending on silicon element. Now, brother of silicon, that is carbon, is playing a major role in science and technology. I will tell you the importance of 1 minute. Just yes. Before going to an introduction part of carbon materials, carbon is having two forms. One is amorphous form and crystalline form. In crystalline form, diamond, graphite, fullerenes, and carbon nanotubes. So within these crystalline forms, fullerenes and graphene and diamond. See, even though they are coming from carbon family, a diamond is an insulator, graphite is a semiconductor, and fullerene and carbon nanotubes are a conductor. That's what, as I told you, the electron will decide the physical and chemical properties of a material. That is, electrical conductivity will be depending on the electronic configuration of carbon and how the structure of the material is. So next, the allotropes of carbon, diamond, graphite, and graphene. This, and I would like to show the model. This is one hexane and pentane, which is having sp2 carbons. Within this, we are having a double bond. This is, instead of showing a double bond, I am having a p orbitals in this model. Just because of these vacant p orbitals, what will happen? Electron will move from one p orbital to another p orbital. That's what graphite is an semiconductor and graphene is a conductor, because graphene is nothing but a monolayer of a graphite. Graphite is an n number of graphene layers. Within that, I am taking one graphene layer, and if you are folding the graphene layer into a round, we will be getting carbon nanotube. This is what the, by structurally they are different. And if you come to the sp3 carbon, this is it is a rigid, and we know very well diamond is a very hardest material in the globe, because carbon-carbon covalent bond is very strong. That's what the reason why a diamond is very strong or very hard, because the carbon-carbon bond is very strong, covalent bond. That's what the diamond is very hardest material. If you come to the graphite, it is a smooth material because of this sp2 carbon. The remaining p orbitals are shown here. You see that each carbon is having a p orbitals. Now what will happen? Electron will move from one p orbital to another p orbital. This concept is known as delocalization of electron. That's what in benzene ring we are writing a ring. That means all the 6 electrons related to 6 carbons. Similarly, the same thing even in carbon nanotubes or graphite or fullerenes, we will be having sp2 hybridized carbon and with vacant p orbital. That's what electron will move from one carbon to another carbon. This is one of the important parameter which will decide the electronic property of the carbon. This is the major difference between diamond, graphite and graphene. We know very well diamond has sp3 as we are, it is very rigid, and graphene sp2, graphite sp2, even carbon nanotube sp2 hybridized carbons. Before going to the carbon materials, I would like to give one of the historical or timelines of carbon and its importance. Then before Christ, that is 326 BC, there's a king called Purushottam or Porus has presented as a knife to the Alexander. The name of the sword is Vuku. That means it is a local name. This Vuku has a carbon material, nano material. That's what that sword has an uniqueness. You see that before knowing the science of, before knowing the nanoscience and nanotechnology, there is an existing science which was not unexplored. This is one of the best example to know the importance of carbon materials. And next one, similarly, you can see Lycurgus Cup. This is an Italian cup which is having silver and gold. This is if you keep light inside, it will be in red color. If you keep light outside, it will be in green color. Because of the size of the silver and gold nanoparticle and the composition of the silver and gold nanoparticle, we are seeing the different colors. Because of reflection, because of refraction and transmittance, we will be seeing these two colors. And why nanomaterials? We have to discuss 3 points before going to the fullerenes. One is electron confinement. As I told just now, the electron movement is nothing but electron confinement and surface to volume ratio and discrete energy levels. 3 things. Second one, that is surface to volume ratio. Before going to the surface to volume ratio, I would like to give a simple example, that is daily life example. You see, these 4 materials are made up of boiled rice, that is boiled rice, idli and uttapam and dosa. But one material will be very tasty because the surface area of dosa is very high. That's what it is very tasty, because we are grinding. Grinding is nothing but we are activating either mechanically or in other form. Just we are supplying energy to the rice and rice is becoming powder. That powder again we are activating. That means we are frying on the heater. That's what dosa will be having very tasty. This is the scientific reason behind in our kitchen, what is happening in our daily life or daily kitchen. And if you come to the uttapam, when compared to dosa, it will have a less taste because the activation, just we are boiling it. And next, if you keep these materials in order, first dosa will come, second uttapam, and third idli, and fourth boiled rice. This is the order of taste. That means dosa will have high taste. You see the rice, 1 kg of rice will occupy 260 meters square. If you come to the grinded powder of rice and after frying, the surface area of this rice powder will be in 200 times of this surface area. That's what, as I am telling, the dosa will be having high surface area. Because of high surface area, those active sites which are present in flour will interact with our tongue active sites. That's what we feel it is very tasty. This is the scientific reason behind in this concept. Again, the charcoal, activated charcoal, if you clean our teeth, because of high surface area of activated charcoal, it will remove even bacterial impurities and color and even bad smell it will remove. That is the scientific reason behind in it. And similarly, sorghum millets. This is 1 kg of sorghum millet will be having 200 meters square. If you grind it, it will have 35,000 meters square per kg. You see, around 175 times higher surface area. That's what this roti will be very tasty. Now, with these 3 examples and the 4th example, we know the importance of surface area, surface to volume ratio. Even when compared to spoon, hand crushed food will be very tasty. That's what our mother feeding food will have a very taste when compared to spoon or other persons, because knowingly or unknowingly, our mother will supply energy to the food and she will crush and she will feed it to the kid. That's what kids will feel. It is in the taste. That is the scientific reason behind in it. This is the importance of surface to volume ratio. And as I told you, next, third one is electron confinement. By seeing this slide, we can understand the importance of nanoscience or carbon materials or carbon nanomaterials, how they are playing major role in nanoscience and technology. The single slide will tell us the evolution of science and technology. Just you see, room size computer has become hand size because of the science and technology or nanoscience and technology, because of the silicon, because of the reduction of size in transistor, because of that we could be able to get hand size computer. This is the importance of carbon materials. Because of the carbon nanotube, because of the graphene, because of the Fullerenes, we could be able to achieve this slide. Next, similarly, the evolution of the telephone. It is from the basic model, that is Alexander Graham Bell's model, to now 2020 model. It is because of the materials, carbon materials and silicon materials, we could be able to achieve the great end model. Next, wheel, invention of the wheel, also one of the top 5. It will occupy the position of within top 5. Because of the composites and nano composites, we could be able to even see the nano composite based car, even nano car we might have. These 4 examples will give the importance of nanoscience and nanotechnology. And even Pistorius, Oscar Pistorius from South Africa, who has carbon nanofibers. You see the importance of carbon nanomaterials. He won World Cup. He became a champion of this thing in 2012 because of the carbon nanofiber. It is like a Fullerene or carbon nanotube or graphene. So now, if we come to the classification of nanomaterials, we are having 4 types of nanomaterials. One is 0-dimensional, 1-dimensional, and 2-dimensional and 3-dimensional materials. For 0-dimensional nanomaterials, Fullerenes are the example. 1-dimensional nanomaterials, carbon nanotubes. 2-dimensional nanomaterials, graphene or thin films. 3-dimensional nanomaterials, carbon microtubes. We will concentrate only on 0-dimensional nanomaterials because we would like to discuss the Fullerenes and synthesis and their applications. So based on the dimension, as I told you earlier, it is based on the dimension we are classifying the nanomaterials. That means if one dimension you are bringing it to nano, the materials, physical and chemical properties will be different. Just 0 dimension, just you see this 3-dimensional spherical material or particle which is having in all the 3 directions in nano size. That's what fullerene will have a spherical size, and we are giving, and fullerene is the example for 0-dimensional nanomaterial. And 1-dimensional nanomaterial, that is carbon nanotube, in 2 dimension, that is in x dimension, y dimension, it is in nano size. In 1 dimension, it is in micron size. That's what carbon nanotubes are 1-dimensional nanomaterials, and 2-dimensional nanomaterials. In 1 dimension, it is in micron size. In x and y, it is in nano size. 2 dimensions, it will be in bulk or microns. In 1 dimension, it will be nano size. This is what 2-dimensional nanomaterial. And 3-dimensional nanomaterials, this is one of the important material, that is carbon microtube. You see how beautiful it was. It looked like carbon nanotube, but the diameter and length, width and height, everything in micron size. This is what 3-dimensional nanomaterial. Now, if we come to our thing, 0-dimensional nanomaterial, we have given introduction to the carbon nanomaterials, and now we are going to discuss about what is fullerenes and importance of fullerenes, and how will you synthesize the fullerenes and properties and applications of fullerene. On behalf of Buckminster Fuller, we have named fullerene. That is, we are having different types of fullerenes. But why this fullerene name has come into the picture? And it's on behalf of Buckminster Fuller. This Buckminster Fuller has designed a dome which is having hexagons and pentagons, as we are seeing in this. He has designed a dome on behalf of his name. Just we are calling these materials, spherical materials, nano-dimensional materials, as fullerenes. Simply, we can define fullerene. Fullerene is nothing but it is a case of carbon atoms. It doesn't have any other atom now. So if it is there, we will call, even though it is a derivative of fullerene, but it is a simple definition of fullerene is it is a case of carbon atoms. Depends on the number of atoms, either C20 or C60 or C70 or C84. We will classify the fullerene. Then in 1996, for discovery of fullerenes, 3 people got Nobel Prize. This single slide will tell the importance of fullerenes. See the types of fullerenes: C60, C70, C84 and C20. C60 will have a spherical like football. The C70 will have a soccer ball shape. A representation of C60 just with models. C60 will have hexagons and pentagons like this. How many pentagons it will be having? Just you see that 20 hexagons will be there, 12 pentagons will be there in C60. See clearly 12 pentagons and 20 hexagons. 20 number of these hexagons and 12 number of. With that, it will have a spherical structure. That is what C60. Okay. If we come to the C70, 25 hexagons and 12 pentagons. Each carbon will have a p orbitals. And now what will happen spherically and 3-dimensionally, we are controlling the electron. Electron will decide the physical and chemical properties, but electron cannot jump out of fullerene particle or molecule. That means these electrons will decide the physical and chemical properties of fullerene. That's what fullerene have a great importance. While discussing the applications, I will tell you the importance of this. And, if you come to the synthesis of fullerenes, KRÄTSCHMER-HUFFMAN has synthesized the fullerenes. In this method, what we do, just we will be having two carbon electrodes, that is, one is anode and one is cathode. These anode and cathode we will be connecting to DC power, and which is having a current of 120 amperes and 25 volts. If you discharge these two electrodes, what will happen? At anode, oxidation will happen. Oxidation means carbon atoms will eject from anode and they will deposit at cathode. You see in this, clearly we are seeing anode as having a smaller size and cathode is having a bigger size. And these carbon atoms will form Fullerene soot on cathode. The collection of this soot and purification of this soot will give us pure Fullerenes. This is a simple synthetic method, just like arc discharge method, and under inert atmosphere condition only we can achieve this. And even if you are having a metals, we will be getting exo or endo Fullerenes, depends on the environment what we are maintaining in this method. Next, extraction of Fullerenes. Pure C60 is obtained by liquid chromatography after synthesizing the Fullerene from method. Just we have to extract it and we have to purify it. What we do, the mixture we will dissolve it in toluene and we will extract C60 alone. Similarly, C70 alone. I will tell you the cost of the Fullerene up to now in the globe. There's an officially C60, 1 gram of C60 will have the cost of 16,500. 1 gram of C70, 1.2 lakhs. And C84 it will be more than this. And 1 gram of endohedral Fullerene, as I told you, which is having a metal inside the Fullerene cavity, is have around 45 lakhs. This is the economical importance. This tells us the importance of C60 Fullerenes. First commercialization of C60 Fullerenes in 1990, the KRÄTSCHMER, which we have seen earlier slides, he has joined with a company called MC, that is Mitsubishi, a company, and they have started selling this C60 Fullerenes in 2007. The properties of Fullerenes, and these Fullerenes have an electron accepting nature. That means they are electron deficient because they are having vacant p orbitals, and now they need an electrons to saturate these bonds. So now what will happen, wherever electron is there, these Fullerenes will go and they will react and they will accept those electrons. That is what Fullerenes are, best electron acceptors. That's what we are using them in organic solar cells. Even organic solar cells, we are using Fullerenes as an electron acceptors. And because of the high crystallinity, and even C60 will show the superconductivity. And a metal can be trapped inside the Fullerene. That's what endohedral Fullerenes. That is metals are always having a tendency of losing electrons to the Fullerene, and Fullerenes are having a tendency of accepting electrons from metal. That's what metals can be trapped physically. And the solubility of Fullerenes, if you see, Fullerenes are normally, it is insoluble in water, but they are soluble in organic solvent. We can soluble these Fullerenes in water by covalent functionalization on Fullerenes. That is the chemical properties of Fullerenes. By knowing the chemical properties of Fullerenes, we can functionalize the Fullerenes and we can even dissolve Fullerene in water. The applications of Fullerenes, you see that Fullerenes are having multi applications. First, free radical scavengers or antioxidants. what is meant by free radical scavengers? Let us take a simple plastic. If you are heating it, it will generate, it will decompose. While decomposition, it will give the free electrons. Those free electrons, if we could able to trap, we can stop the decomposition. If we add fullerene to those polymers, we can stop the decomposition. That's what the oxidant. Fullerenes are the best free radical scavengers. And fullerenes are best electron acceptors. That's what we are using them in organic solar cells. And even UV visible NIR protection, if we want to protect our eye from UV visible and NIR, we are using them in protecting material. And fullerenes are anti-cancer agents, and fullerenes are by consuming the fullerene in olive oil or oleic acid, we can increase our lifetime. This is still research is going on, but people are not consuming directly. But already clinical trials suggest that lifetime of the human can be increased by consuming the fullerene along with oleic acid. And neurodegenerative treatment, in that also we can use fullerenes, and cardioprotector and apoptosis inhibitor. That means fullerenes doesn't allow the apoptosis process. That means cell division. Cell division will not happen. If fullerene is there, it will stop the apoptosis process. And this, based on this concept, the lifetime of an human or a rat, we can increase maybe 80 to 100%. Instead of 50 years, we can survive even 100 years, maybe in future. And even in MRI scanning, we are using gadolinium fullerenes as a contrast agent, and we are using as a dry lubricant in automobile industry in drug delivery, because fullerenes are having around 2 nanometer size, and it can enter into any cell. That's what fullerenes, by covalent functionalization of your polymers or your target or drug material on the fullerene, and fullerene will take those drug molecules and it will deliver in the respective place where we want to deliver our drug. See, as I told you, lifetime of rats. Lifetime of rats, this blue color water treated rats and red color olive oil treated, and olive oil and fullerene treated 66 months, around 38 to 66 months. Life expectancy or lifetime of the rats was increased around double. 80% of the lifetime was improved by treating it with the fullerene and olive oil. And even some of the countries, people have started commercially selling this fullerene and olive oil mixture, and even they can apply it on skin. And because if you are applying it on skin, what will happen? Any free radical or any reactive species which is attacking on our skin, what immediately this fullerene will nullify it, or it will react with that electron and it will stop the oxidation process. That is then science. As I told you, free radical scavenging capacity. That is the one of the important property of fullerene. Second, even fullerenes for health sector, if you in drug delivery, because of the 2 nanometers size, fullerene can deliver the drug into the blood-brain barrier. Even you see that there's an fullerene can carry the drug directly to the blood-brain area, and apoptotic cell death can be controlled by fullerenes. Fullerene will stop the apoptosis process, and it will be acting like a protective layer of DNA. And these are the multiple applications of multiple nanomaterials. Next, applications of fullerenes in medicine. There's an almost, we have discussed every application. Fullerene derivatives are HIV inhibitors. Even fullerenes are antiviral agents. It is having a spherical structure, and the diameter of the fullerene is 1 to 2 nanometers. That's what it can penetrate into the cell wall, and it can stop the oxidation process by consuming the electron, where the electron transfer reaction is happening. There, what it do, this fullerene will take that electron and it will stop the oxidation process. That's what the replication of HIV was stopped by fullerenes. And what these fullerenes indirectly will do, it will impair the protease activity. The protein, because of the protease activity, HIV replication will happen. Indirectly, it will stop the, it will impair the protease activity. That is the fullerene activity. That is, this is one of the antiviral action of fullerene. And in organic solar cells, these fullerenes will act like an electron acceptors. This is the one with